Welcome to my YouTube channel. Today I am going to discuss the velocity diagram for the impulse turbine blade. So for this we'll give some concept and we'll discuss the formula. Then next video we'll solve the questions. So before the drawing the velocity diagram, some concept we have to know. So why we are studying the velocity diagram? So I wrote some theory parts here to determine the rate of change of momentum of the steam, because once blades will run, how blades will run? Because we have to supply the steam through the nozzle. So that's only there to determine rate of change of momentum of steam across the moving blade. So velocity diagrams we can draw only moving blade, because steam will inject to the moving blade only. So that's why I wrote steam across the moving blade in order to find the forces on the blade. Power we can determine for this. Blade velocity we can determine. Suitable inlet and outlet angle can be evaluated. Then in impulse turbine, relative velocity of steam always remains constant. In impulse turbine, what will happen? Relative velocity will be always constant. That is called VR1 equal to VR2. So we taken symbol the relative velocity VR. So VR1 inlet velocity, relative velocity at inlet, relative velocity at outlet. Both will be equal in the impulse turbine, when blades will be the smooth surface. But actually it will not be the smooth surface. Suppose we will consider smooth surface now, then relative velocity will be equal. But but actually always a certain loss of the velocity, because once the steam will enter into the blade, some loss will be there in the velocity during the flow of steam over the blade. In that case, relative velocity at inlet will be greater than the relative velocity at outlet. So what will the blade velocity coefficient then? VR2 by VR1. So here two cases will be there. Suppose blade with the smooth surface, relative velocity inlet and outlet will be equal. But if we'll consider the loss of velocity when the steam flow through the blades, then relative velocity at inlet will be greater than the relative velocity at outlet. So that is blade velocity coefficient will be VR2 by VR1. Some important notations I given here. Once I draw the velocity diagram, these notations we will follow. So different books we have different notations. So just how to understand the velocity diagram, for that notations I given here. So first we'll draw the velocity diagram for the moving blade only. So here already we started. So this is the moving blade. Impulse moving blade. Because we are not talking about the reaction turbine, we are talking about the impulse turbine. So impulse blade we taken. So one impulse blade we taken. This is inlet triangle. This side is the outlet triangle. So we'll see that steam will enters into the blade by the some specific nozzle angle. So alpha we taken the nozzle angle. Now this is the relative velocity, absolute velocity. V symbol we taken the symbol absolute velocity of steam at inlet. Now this is the theta we are considering, that is inlet blade angle. So I wrote here inlet blade angle. Theta will be the inlet blade angle. Then inlet blade angle will come to the inlet outlet blade angle phi. So this relative velocity we are giving at inlet, relative velocity at outlet. This is the relative velocity at outlet. So theta is nothing but inlet velocity at given a inlet blade angle, phi is outlet blade angle. VR1 relative velocity at inlet, relative velocity at outlet. Again here beta, nozzle angle at outlet beta. So this is the steam velocity at outlet. Then this is the flow velocity. Flow velocity at inlet, flow velocity at outlet. Now what we will see here? Vril velocity we will see. Vril velocity will be up to this only. This is called vril velocity, WV. Vril velocity at inlet and velocity at outlet. So this will right here. And this is the blade velocity. Here. VB symbols I taken somewhere. Absolute velocity of steam, blade velocity, absolute blade velocity. So these symbols I am taking is small VB. This is VW1, real velocity at inlet. This is blade velocity at inlet, you can pay. Now, here also will be the, this will be the angle of the blade velocity at outlet here. This is the blade velocity at outlet. V small VB2. And this is the real velocity at outlet. Real velocity at outlet. Okay. So this will be the center here. We can just, these things not that much required, but this is the origin. This is the tangent. This is the tangent. So axial flow velocity will follow the axially. So what we have to see, the inlet angle, alpha nozzle angle enters into the outlet blade angle. Beta will be the nozzle outlet angle. Theta is the inlet blade angle. Outlet blade angle, relative velocity at inlet, relative outlet. Steam velocity at inlet, steam velocity at outlet. So now this is the velocity diagram. Now what we'll do, this velocity diagram will, inlet and outlet triangle will combine together. What we'll do here, we'll combine together inlet and outlet velocity. So this is outlet velocity, we'll write here. Outlet velocity, outlet triangle. Now what I'm going to do here, just I'll draw the little bigger diagram. So inlet and outlet triangle will combine together, we'll get the velocity diagram. So first this inlet triangles will draw here. We'll draw this, what is the inlet triangle here, so that we'll draw here. Inlet triangle I draw here. This is the inlet triangle, what we draw here. So this is the blade velocity theta, blade velocity theta, blade velocity is the inlet blade angle theta, nozzle angle, this will be the real velocity, this will be nothing but real velocity at inlet, this is the blade velocity at inlet, this is the flow velocity, this is relative velocity inlet, steam velocity at inlet. Now we'll combine the outlet triangle here. Now you look here, theta is inlet blade angle. So inlet blade angle, then outlet blade angle will come here. Inlet blade angle, this is called outlet blade angle we draw. This outlet blade angle we draw here. So this is VR1, then what will be this is VR2. How to combine this? Actually this angle, this you inverted, you keep it here. Inverted, so that only we are going to do. But what is the easy method to draw the velocity diagram? Inlet blade angle, outlet blade angle. Now nozzle angle at inlet, nozzle angle at outlet. So nozzle angle this one, so nozzle angle at outlet. Extend this, it will go the vertical line. If we'll extend this, if we'll extend this line, what is this one? Real velocity at, it will be real velocity at outlet. You can write here VW to real velocity at outlet. So this is the VR2, this is the V1, this is VF2, this is VF1, this angle will be beta, this angle will be beta. So what we did here, this inlet triangle, now this outlet triangle we kept there. So how to draw, you see here again, theta will be the inlet blade angle. This is phi. Phi will be the outlet blade angle. This inlet blade angle coming out the outlet blade. So inlet angle coming out the outlet angle. Now alpha nozzle angle is coming out the outlet angle. Now draw the vertical line, we'll get the VF2. So flow velocity at outlet, flow velocity at inlet. Now what we'll see this blade velocity? Blade velocity VB1 is equal to VB2. Both will be equal. Both will be equal. So we can say this is the VB. This we can see the VB. VB. Blade velocity at inlet, blade velocity of outlet, both will be immersed. That will be coincide. So this blade velocity always will be equal for equal. Now some notations, you check it again. Steam enters to the nozzle angle and outlet will be the beta will be the outlet nozzle angle. Inlet blade angle, outlet blade angle. Relative velocity at inlet VR1, relative velocity at outlet. Flow velocity at inlet, flow velocity of outlet. Then absolute velocity V1, absolute velocity V2 at outlet. Now what will be the possible formula here? What will be the possible formula here? If we'll find the tangential thrust. Tangential thrust nothing but mass flow rate into vril velocity, change in vril velocity. So mass flow rate, M is what nothing but, M is mass flow rate. Mass flow rate, that is called kg per second. Kg per second. Mass flow rate into change in vril velocity. One minute. So what is this one? For possible for tangential thrust. Tangential thrust nothing but mass flow rate into change in the vril velocity. Why we taking the plus minus? Once we'll solve the questions, this plus minus why we taken, let's see here. If beta less than 90 degree, then VW2 will be the positive. VW2 will be positive. See here, beta is less than 90 degrees, so VW2 will be there. So that is positive. If beta will be 90 degree, this 90 degree, this V1, it will come the vertical line. It will come the vertical line. Actually, you listen here. This is the inlet blade angle. Now beta, if this beta will be 90 degree, what is VW2 here? VW2 will be 0. VW2 will be 0. And if beta greater than 90 degree, in that case, V2, so this will go the vertical line, this will come inside VW2. So VW2 will come negative. VW2 will come negative. When we will solve the question, these things will discuss according to the given data of the problem. So this plus minus why it taken? Suppose beta is less than 90, we will take the plus. If beta will be more than 90, we will take the minus. If beta is 90 degree, then VW2 will be 0 everywhere. Where will the vril velocity? Will be the 0. So according to these conditions, this formula will change. So tangential thrust nothing but m into vril velocity plus minus inlet and outlet. Unit will be Newton. How unit will be Newton? See, mass flow rate kg per second. And what is velocity there? Meter per second. Kg meter per second square. If you will see this kg meter per second square is known as Newton. So that's a force. Tangential thrust is Newton. Now this power or work done per second. Work done per second also you can say here tangential force into blade velocity. Tangential force what is? This is the tangential force into blade velocity VB. You can, this symbol give the VB. Tangential thrust into blade velocity is known as work done per second or power. So this unit will be meter per second. kg per second, meter per second, and meter per second. So what will come here? See here, kg per second, then one velocity meter per second, blade velocity meter per second. Kg meter per second square is known as Newton meter per second. Newton meter means joule per second. Then joule per second is nothing but watt. So what is unit here? Watt. So power unit will be the watt. This is a possible unit will be there. We have to, sometimes mass they will give kg per hour, kg per minute. According to this we have to convert the kg per second. Mass should be kg per second, velocity meter per second, velocity blade velocity meter per second. So you can come this way, it will come the power unit is watt. Now kinetic energy per second, half mv1 square. So always we'll take the kinetic energy, we'll take the steam velocity at inlet only. We'll take the inlet velocity only. Once we'll take the kinetic energy first, we'll take the velocity, absolute velocity of steam at inlet only. Then what is the diagram efficiency or blade efficiency? Diagram efficiency or blade efficiency. Symbol is this efficiency. So work done by kinetic energy per second. Work done by kinetic energy per. What is work done? mvw1 plus minus you can write here also vw2 into vb. So you can write blade velocity vb because blade velocity and inlet outlet will be equal. Half mv1 square. So get cancelled, 2 will go the numerator, 2 vw1 plus minus vw2 vb by v1 square. So always this v1 square we will take absolute velocity of steam at inlet only. So this is the diagram efficiency. What is the axial thrust? M into difference of the flow velocity, vf1 minus vf2. So this is the possible formula is there to solve the steam turbine problem, for the impulse in steam turbine problem. So what is the meaning there? If we draw the tentative velocity diagram, according to the problem, this velocity diagram will change according to the given beta. Beta angle, acute angle, then it will take plus, beta is greater than, minus, if beta is 90 degree, vw2 will not be there. So this part will get 0. So according to the changes will be there, and according to the velocity diagram also will change it. So what we'll do the next video, this basic concept I given for the velocity diagram for the impulse blade. Then we'll solve the questions by the schematic method and also with the graphical method. Both method will solve, and this is the possible formula. We'll substitute and we'll get the value. So schematic method, now how we'll solve the problem. So you will see here. You will see here what is, just 1 minute here also I will show you. So this theory part I will review it. So see here what will be there possible schematic method. Here how many triangle will be there? 4 triangle will be there. So first we'll take this is alpha triangle. Then this will take a theta triangle. Then another will be phi triangle. This will be the phi. Then another triangle will be beta. So these 4 triangles will take out from this velocity diagram. Now all the triangles will be right angle triangle. All the triangle will be right angle triangle. All the notations will write here V1, VW1, VF1. So this will, what will come? VW1 minus V1, VW1 minus VB. Then this is VF1, this theta will be VR1. Now phi. Phi means VW2, this is phi. VW2 plus VB. This is VF2, this phi will be VR2. Now beta, VF2, VW2, this is V2. This is here V1, this will be the V2. This will be here outlet angle. So all 2 symbol will be outlet angle, 1 will be the inlet blade angle, V2. So symbols will be helpful, V1, V2. So why I did this? Because if you have seen this formula, all the velocity will be the unknown. Either VW1, either VF1, either VW2, all the velocities will be the unknown. So what will be generally given? So generally steam nozzle angle and steam flow, absolute velocity of the steam they will give. Because steam will flow through the blade, some velocity should be there and some angle will be there. If these two they given, alpha and V1 given, angle and one side given. What is Pythagoras theorem telling? Suppose we will take the sine alpha. Sine alpha is equal to nothing but P by H. VW1 by V1. If we will take the cos alpha, B by H. Sine alpha is equal to P by H. So VF1 by V1. Cos alpha will take the B by H. B by H. Because this is the angle, so this is the base. B by H. Tan alpha will take tan alpha P by B. So VF1 by VW1. By the Pythagoras theorem, we know the sine cos tan. So this way, suppose alpha given, V1 given, VF1 we can calculate, VW1 we can calculate. Similarly, this triangle, all this method will follow. All this method will follow and find the velocity unknown. All the unknown velocity will find and will substitute these equations according to the given conditions. We will get the solutions for the steam turbine. So this is the key point for the velocity to the impulse blade. Velocity diagram for the impulse blade, and can solve the questions. Okay students, watch this video carefully. Revise once and twice. Next video I am going to solve the question. So this knowledge required that times. Okay. Okay students, thank you.